Alright, what's going on, guys? Today we are going to start talking about the density matrix for closed systems, and then we're going to move on to talking about the density matrix for open systems in the next video on this topic of quantum statistics. We're going to do this from a very first principles perspective, and so without further ado, let's go ahead and dive into the material. So keep in mind that there's notes that are going to be published on my Patreon page if you guys want to get the full notes for all of this. So this is going to be an important note that the density matrix has multiple representations. We've talked about this, or we've mentioned it in the last video. Now we're going to bring it back. Now we're going to talk more about the density matrix, and we're going to see how it fits in with this idea of von Neumann entropy, and what we're going to do after we talk about closed quantum systems. So let's consider an ensemble A. This is just one ensemble. Again, an ensemble you can think of as being the number of copies of a system, and those copies have some label on them, and that label is attributed to some statistic or some quantum intrinsic property, right? So spin, for example, is the typical one that we all think of. And spin, we can consider a two-state system here, and the two-state system is going to be spin up, spin down. So spin up, or we'll call spin down this 0 state, and we'll call spin up this 1 state. All right. And so the fraction of the ensemble that is spin down, or the number of copies, if you will, in the entire ensemble that's spin down, is going to be P. That's related to the probability by which we observe that observable about our system. And then 1 over P is going to be the probability by, or 1 minus P is going to be the probability by which we observe the state in that's not spin down, right? So it's going to be, we have P and then 1 minus P together, they sum to 100%. And so this is a very simple ensemble, and we can construct our density matrix. Our density matrix looks like this. So this is our up state, or our down states, right? These are going to be our down states. This is the up states. And then we have our probabilities in front of them, or our fractions in front of them. Alright, so now let's consider ensemble B. Now, what's going to be interesting about ensemble B is that it's going to have the same density matrix, and we'll see how this works. So so we have a state U and we have a state V. They're not up and down states. However, we can define them as being superpositions of up and down states, as we've sort of alluded to in the last video as well. So we're going to define U as being a superposition of up and down, right? So this is our down state, right? This is our up state. And we have the square root of P and the square root of 1 minus P in front of these. For V, it's just going to be the difference between the two. Okay? So these are superposition states. They're not up and they're not down states. They're a combination of the two. So we're allowing our system, if you can sort of picture this, if we're allowing our system, we have a particle, say, has spin up, or a particle can have spin down, or it can be in a superposition of the two, right? So our U state, for example, could be something like, so this would be our 1 state, this thing would be our 0 state, and our U state would be something like, how can I do this? We have a particle, and it's in a superposition between up and down, okay? And then our V state is also in a superposition of up and down, just a different, it's mathematically different, right? Instead of, we have this plus sign we have the minus sign instead of the plus sign. And so we have, again, a superposition of up and down states. And these are vectors. These are represented by vectors, right? This is a bra vector, or these are the ket vectors, right? These are all ket vectors. But we can also use the ket version. The ket version of these vectors is just going to be, since there's no complex numbers here, it's just going to be, when we take the outer product between the two states, we get this, right? This is our ket vector, and then just bra vector and bra vector. Nothing about the coefficients changes because they're not complex, or they're not Hermitian or anything like that. And so what we can do is we could say, now we multiply all this out, right? So this times this times this right here, and so forth. And so we get all of this. And because up and down are orthogonal states, these guys here will go to 0, right? And so we get this right here. We just multiplied both sides by 1/2, and we'll see why we do that in a few minutes here. But the idea here now is that, okay, we have this right here is equal to this. In a similar way, we can do the calculation for the v state, right? So that's going to be this guy right here, same thing right here. And so, okay, this is strange. So we can add this and this together, which means we're going to add this and this together. And when we do that, this is just half of this thing plus the other half of the same thing. That's going to be 1. Well, this right here, is the same thing as this right here. So we have two ensembles, right? So we have two ensembles. They both have the same density matrix, which is kind of strange, but one is pure states, right? We have up and down, pure states. The other is an ensemble of superposition of states. And they both have the same density matrix. So something weird is going on here. We've seen with this example that the density matrix is the same for ensemble A now as for ensemble B. And so there's no way to distinguish between these two ensembles by any sort of physical measurement. This is, again, because our density matrix times some arbitrary, the trace of the density matrix multiplied by some arbitrary observable, A, is going to be the same for any observable, because, again, these matrices here, these density matrices here, are the same for ensemble A and ensemble B. So, again, we can't, because we're multiplying x by A and x by B, where x is the same in both situations, and so we can't, there's nothing distinguishable between the two. So, okay, this is weird. So to resolve this issue, we need to see what the dynamics is for each density matrix. If this is the case, that each representation has different dynamics, then we'll be able to distinguish between both cases of the ensembles. So this is going to bring us into the realm of dynamic density matrices. So in the quantum case, the goal is to assign an entropy to a density operator. But the problem here is that each density operator corresponds potentially to an infinite number of different ensembles. So we have our density operator, or our density matrix, rho. It can be like 1/2, 1/2, 1/2, 1/2, like this. It can look like 1, 1, 0, 0. It can look like something else. It can look like something. So the density matrix has different representations. Okay, this is gonna be a problem for us. But what we'll be able to see is that what makes these representations unique is their eigenvalues and their eigenvectors. Okay, and we'll see how we can use the eigenvalues and eigenvectors to our advantage to be able to distinguish which row matrix to use in certain cases. Okay, so this is where the John von Neumann entropy comes into play. Fundamentally, the way in the language that we're talking about, von Neumann entropy is an entropy of the eigenvalues of our density matrix. Okay, we'll dive deep into what exactly these eigenvalues, how we can make sense of them physically later. But let's just get some example problems under our feet so that we can be able to make sense of this before we go any further. So John von Neumann proposed that we choose a special decomposition, and we'll call it the orthonormal decomposition, or the OD. Okay, so what is the OD? Well, okay, here it is. This is our OD. This is the prescription that we're going to use to understand how we can make sense of the density matrix, or the orthonormal decomposition of the density matrix. This is one specific decomposition of the matrix, and that specific decomposition of the matrix is what we're going to use to define the von Neumann entropy of our system, or the entropy of our quantum system. And so to do this, he said, okay, rho, our density matrix, acting on some vector phi n, is equal to just some scalar number times phi n, which means that phi n is the eigenvector of rho, and the lambda here is the eigenvalue for rho. Okay, and rho can be regarded as the sum of the outer product between its eigenvectors and its eigenvalue, and we're going to say that the fraction here is going to be equal to its eigenvalue, right? So we can write this then is phi n like this. All right, this is going to be key here, and so okay, let's continue, and we're going to say that the inner product between any two eigenvectors is going to equal to the Kronecker delta, and that's just to say that they're orthonormal or orthogonal to each other. Orthonormal means that I won't get too much into that. It's not too important for right now. But anyways, what is special about this density matrix is the states here are eigenvectors of the density matrix, and where the eigenvalues lambda n are eigenvalues of, or are the eigenvalues of the density matrix. So now we're going to define the von Neumann entropy. The von Neumann entropy looks like this. Okay, and I'm suppressing the KB here. Suppressing this KB because just to make our life a little bit easier, we don't have to follow things around too much. But fundamentally, though, the way we're defining this is in terms of the eigenvalues of our density our density matrix. So, because again, lambda n, these are the eigenvalues of the matrix. So let's do an example. Let's do a simple example to illustrate how this is going to work. So let's do an example. This is for our von Neumann entropy. Let's suppose that our ensemble is in a superposition of states. Right. So this is a vector. And we're going to say that this is an eigenvector of rho. Right. So this is to say that suppose we have something that we have two eigenvectors, phi n and actually let's phi n and phi m. This is going to be Kronecker delta, right? Because they're orthogonal to each other. But that's the one thing that we want to do here is actually see that in this basis, the 0, 1 basis, we can't make that assumption. We cannot make the assumption that 0 and 1, suppose this is up and down states, that say that this is down state and this is up state, and we cannot make the assumption that these guys are going to be orthogonal to each other in this case. And when we do that, we're going to see that these two elements here don't go to 0. And you can see this, right? So when we do this, we can construct the density matrix in this way, because again, we're saying that this here is the eigenvalue, or the eigenvector, not these guys. And so when we do that, we do this, we get this, and then these guys, because we're not going to make that assumption that these guys are orthogonal to each other, we get the row matrix that looks like this, or the density matrix that looks like this. And this density matrix then, we get this 1/2 because we have, again, this guy here is going to be associated with that entry, this one here with that entry, this one with that entry, and this one with this entry, and we have this 1/2 in front of all of them. All right. Here we did not make the assumption that in that basis, or the up-down states, that was an orthogonal basis to the ensemble. To calculate the von Neumann entropy of this density matrix, all we need to do is find the eigenvalues of the matrix through diagonalization of the matrix, which is a topic for linear algebra. I'm not going to go too much into this because linear algebra is something that I'm assuming you've taken, given that you're looking at a video on quantum statistics, which I think is probably a lot more, I wouldn't say a lot more advanced, but it requires the use of linear algebra. Then we plug our eigenvalues into the von Neumann entropy. So to do this, we just plug in our eigenvalues, right? So our eigenvalues for this matrix are 0 and 1. So we have lambda 1 and lambda 2. This is going to be 1 and 1's going to be 0, and so we plug these guys into our von Neumann entropy, and we get that the von Neumann entropy is 0 for this system. So with this matrix right here, with this density matrix and this superposition of states in this basis, right? So in this basis, we have that our von Neumann entropy rho, say in the psi basis, is equal to 0. And then, so as we go forward in this playlist, we're going to see what happens when we change this to a different basis. But so far, what we have is a way of defining the entropy of some quantum ensemble with the density matrix. So given some density matrix, visually, we might be able to see that in the following way for a simple two-state system, we have a density matrix that looks like this, right here, and these guys here, the off-diagonals, are the superpositions, where the on-diagonals are the pure states. These are the states that we measure, and finding the eigenvalues of this matrix collapses it into weights associated with just the completely real parts. So that's going to be the diagonal parts. And the diagonal parts then, I've made these smaller because one eigenvalue might be larger than the other, and that might correspond to higher probability in observing an upstate than a downstate. So the von Neumann entropy is like an entropy of eigenvalues of the density matrix. This is not the same thing as the standard entropy that we are familiar with. In fact, von Neumann entropy will run into a few problems, namely that it's not always increasing. And that's going to be a very interesting sort of caveat to this idea of von Neumann entropy. Neumann himself was regarded as somewhat of a genius in his time, and so even though there's problems with this, he was still very much a titan in the area of quantum statistics and many-body physics. But let's continue. So let's now consider the time evolution of our density matrix for a closed quantum system. Such a system will be considered to have all of the fractions or probabilities be the same during the time evolution. This is to say that nothing interacts with the system to change the probabilities or fractions over time. Again, this is to say that P1 at time 0 and P2 at time 0 remain P1 and P2 at time greater than 0. And our states, I'll call this phi for right now, just to be consistent. At phi 0, these are going to be the eigenstates of our matrix. All right. These are going to be eigenstates, and then we have eigenstates at 0, go to eigenstates at t, and these we're allowing to be complex, and so we say they time evolve according to this time evolution operator. All right, we're going to be very general right now. Later we'll actually get into some specifics. We'll see how we can use this actually for MRI physics. With MRI physics, we'll be able to see, because the idea behind MRI physics is you have a particle in some tissue, and it's got, say it's down in its state, and you probe this with a magnetic field B, right? So you have a constant magnetic field, and then you provide a pulse of how do I want to do a pulse? I want to illustrate a pulse maybe like this. This is normally how you see it in MRI physics. A pulse is going to be applied to our system of some sort of another external magnetic field, B, or maybe something else like an electromagnetic field, H, for example. But this pulse is going to be applied, and when the pulse is applied, the particle goes to an upstate. Okay, it goes to an upstate, and then after the pulse is done, it relaxes back down to the spin down state, and as it relaxes back down, what happens is energy is released in the form of photons, say, and we can measure that. And the rate of release is going to be given to us by these T1 and T2 variables, as we'll see later. these are very important variables when it comes to understanding MRI physics. And we'll be able to actually derive these mathematically with their expressions in the context of MRI physics, because fundamentally, what we want to do with physics is we want to be able to apply it. Applied physics is how we go forward in society, right? At more advanced technological advances in our society are what drives society to go forward. And so to understand how all this works from basic principles of statistical physics is fundamentally required for us. But anyways, this is somewhat of a diverging thing, but we'll get back to it. We'll understand how we can use these ideas in quantum statistics to make sense of MRI physics. We're going to allow the states to evolve according to an arbitrary time evolution operator, and this operator we say will obey Hermiticity to behave like a quantum operator. So upon demanding that this operator is Hermitian, we can see that the density operator time evolves in the following way. So here is our time evolution of our density matrix. So here's our density matrix T, and the density matrix T can be written in this way. With this, again, this is the outer product of two eigenstates, and then we have the outer product of our two eigenstates. Again, they're time evolving, right? So this should be time evolving, and so this one time evolves according to the Hermitian conjugate of this guy right here. This guy is acting on this guy right here. These are the eigenvalues, and so what we end up getting is that this right here, right? Because this here is just rho of time equals 0. Okay. And this is a special case of what is known as the Troy-Krauss representation theorem. The Troy-Krauss representation theorem looks like this, and we're going to actually derive this, but the point here is that introducing the gamma subscript, this is going to allow us to break free from the matrices having to be unitary. And the only condition that we're going to require is just that the sum over these gammas will be equal to 1. And we'll see more about this later. When we start talking about having quantum systems be open, be available to the outside environment, which is going to change their probabilities and everything, this is going to really help us in understanding how this evolves, how this rho matrix or how this density matrix evolves in time. At all times in this closed system, the density matrix remains in its orthonormal decomposition, as we can see with the following calculation. So again, this guy here, at time t and at time t, well, we allow them to evolve. These two guys are unitary operators. Again, this one acting on this one, and this one acting on this one. And so, because these are two unitary operators or Hermitian operators, the Hermitian conjugate of this will give us 1, and so we just give this, and we get this. So the density matrix is changing, right? So the matrix is changing, but this here tells us that the eigenvectors are also going to, they're not going to, right? So the density matrix is changing because the eigenvectors are changing, but the eigenvalues are going to stay the same for the closed quantum system, right? Because I was about to say that these change, but they also about to say that they don't change because of this, but they do because this is just an inner product between the two. So this is to say, again, that the eigenvalues are going to stay the same. And again, because the eigenvalues represent the fraction of the number of states, or the number of copies of a state within our ensemble. And so for a closed quantum system, and this is really what tells us that we have, for our density matrix at some time t, the von Neumann entropy looks like this, but this doesn't depend on time. This thing right here doesn't depend on time, or these fractions don't evolve in time, right? And so because the fractions don't evolve in time, this is equal to our density matrix at 0 as well. Or the entropy of our density matrix, the von Neumann entropy of our density matrix as well. So again, so the idea here is that in a closed quantum system, we allow for the eigenvectors to change, but the eigenvalues, which are the fractions, those don't change. Again, this is in a closed quantum system. So in a closed quantum system, eigenvectors don't change, or eigenvalues don't change, my apologies. Eigenvalues don't change because we're not allowing for the fraction or the number of copies of our state or of our system to be influenced by outside factors. Okay. If we, this is also fundamentally different from the entropy that we all know and love from thermodynamics and chemistry, right? Because in chemistry, the entropy is defined by the number of microstates of a system, not the number of copies of a system in an ensemble. So this is going to be a very important distinction to make. The eigenvalues of the density matrix allow us to consider eigenvectors that lie in the complex plane. Such matrices encapsulate all of the information that is required to understand the possible superposition of states in our system. So the next thing that we are going to want to ask now is, what will happen when we consider open systems? In other words, what's going to happen to the time evolution of our density matrix when we allow our system to interact with its environment? And with that, we will conclude, and we're going to start going into how we might be able to reconcile things with open systems. And again, so open systems, those are going to, again, allow for the number of fractions, or for the fractions to be influenced by the outside world. Just to picture this again, we have copies of our system, right? So suppose we have 5 copies of our system in an ensemble. Here's our total ensemble. Ensemble. And suppose we have spin up system, spin up, and then spin down, and spin down. So this fraction is going to be P, and say this fraction is going to be P minus, or 1 minus P, right? 1 minus P. And for a closed system, these numbers stay the same. Okay. For an open quantum system, we're then going to say, we're going to allow for stuff like this to happen, right? So the number of down states, the fraction of the number of down states can increase or decrease. The fraction of the number of up states can increase or decrease. And then, when we start talking about many particle physics, then we start getting into considering sort of net spins, if you will. When we start getting into the Ising model and all that. But with that being said, make sure to hit that like and subscribe button, and I will see you guys in the next video.